All right, in this video what we're going to do is we're going to unpack the minus sign that shows up in Faraday's law. So here I've written Faraday's law in two ways. One in the electric field statement with this non-coulombic or curly electric field. And the other way is thinking about the current that actually would run in a loop of wire. And the way we're going to unpack this is actually to understand this particular example that I have over here that we'll talk about. But what's interesting about this minus sign is that it's super important. If it weren't there, we'd actually have a perpetual motion machine. We'd have a problem with conservation of energy. We'd have a problem with conservation of linear momentum. And all of that comes to bear in this particular example. So this example here is essentially two rails that are connected by a wire. So you have this sort of U-shaped set of rails. And there's a metal bar that runs along the rails. And this is a frictionless situation, or that it can run along the wire. And there's a magnetic field that points everywhere into the page. Okay? So given that the bar will just sit there, nothing will actually happen and we won't see any current running. But we can give the bar a little kick. So let's say we kick it to the right, we give it a little velocity to the right. And so after some amount of time, the bar will have moved to the right a little bit. And we'll have some additional magnetic flux in the loop that is these three sides of the wire and that bar, right? We have sort of opened up the loop a little bit. We've changed the area. We've made it a little bit bigger. If you really wanted to sort of keep track of this, right, so you could think of this as if there's some initial length here, and then this has some height, and there's some final length here, and there's some height associated with these guys, then the initial flux is going to be something like the magnetic field times the initial length times the height, and the final flux will be something like the magnetic field times the final length times the height. And because the length in the second case is longer, there's more magnetic flux, right? And so what happens here is that the current that develops in this wire will run in a way to produce a magnetic field that opposes the change in flux. So what we observe is that nature sort of abhors changes in this way, right? So it likes the status quo. And so what is being done here by the electric field that is produced as a result of a changing magnetic field is that you drive a current so that you produce a magnetic field that points opposite the direction of the change in flux. And so because we have an increased flux, we have a magnetic field that is going to try to point out of the board to decrease that flux. That is, the current that develops will point counterclockwise to produce a magnetic field that points out of the board. So let's see how that is. So the way that we're going to understand that is we'll use a technique called the right-hand rule, but it's a slightly different right-hand rule. So in this case, the magnetic field points into the board, and it gets a bit larger. The flux gets a bit larger because we essentially open up more area. And so as a result, the change that we're seeing is the result of a sort of larger magnetic flux, which comes from a magnetic field pointing into the board. So we point our thumb in that direction to indicate that this is increasing. Now, what happens is that because the natural system is trying to essentially oppose that change, we have to flip our hand over to get a sense of what the wire is going to do. So it's going to try to produce a magnetic field that points out of the board to reduce the overall flux. And so our fingers will then curl in the direction that is going to produce the electric field or the current that is driven through that wire and bar to make the magnetic field that reduces the flux. And so once we kick this thing along, there's going to be a current that develops that runs around the wire this way in this loop. And that's actually the direction roughly that the electric field will point as a result. And so what we get is we get this driven sort of system that a current will develop in here to produce a new magnetic field that points out of the board and tries to reduce the overall flux through that loop. Now that sort of combination of things has its own sort of statement. This idea that nature abhors changes in flux, or that, essentially the currents are driven in ways to reduce the overall flux change and so forth. And that thing is called Lenz's law. But it's really nothing special. It's just a statement of what Faraday's law does in sort of a compact way. It does this opposition of the change in flux kind of thing. Now, what's really interesting about this is that as this bar moves along, it's actually going to slow down. So let's make sense of that, because this is where that minus sign really comes in. Because what we found here is that the current will develop in the wire this way because of that minus sign. So if we look at the loop here, we have a bar that is moving to the right but has a current that goes up like this. There's a magnetic field that everywhere points into the board. So I'm only going to draw a few of these. And if we go back to our statement of magnetic force, which is IL cross B, the I points upward, so that's the direction of L. The B points into the page, so the right-hand rule tells us that this bar will experience a force, a magnetic force, back that way. And because it was kicked to the right, it's going to be slowing down as it moves across, which is really nice. We gave the system some energy, and that energy is being used in that system to sort of drive this wire along, or sorry, drive the bar along, but it's also getting used up. This magnetic force is essentially using that energy up. It's being converted to magnetic energy associated with driving the current around. And so if we didn't have that minus sign and the current went the other direction, that'd be super problematic because the force would point to accelerate the bar across in the direction of the velocity, and we'd be able to get this sort of infinite amount of energy by just setting up the system and flicking a little bar across. And that's not how nature works, right? It's not, you're not going to get anything for free. Okay? Now, I think what I was worried about this is that it looks to me like we just said that there's a magnetic force that pushes on a bar and slows it down, right? So what we're saying by stating that is, it looks like, anyway, what we're saying by stating that is that the magnetic force is doing work on that bar, right? It's changing the kinetic energy of the bar. And this is typically how this is taught, by using this to talk about sort of what happens to the bar, and you sort of sweep it under the rug a bit. But it's problematic because we know that in this sort of classical sense, the magnetic field can't do any work. So what is actually reducing the speed of the bar as it goes along? Well, as the charges that are actually moving in this wire move along, they're moving in a frame that moves both to the right, and they are moving up. So they're actually taking a path that is a little more complicated than we've sort of set up here. And so these magnetic forces that these individual charges actually experience actually turn them a little bit, and they build up on the sides of the bar. And then there's an electrostatic repulsion that occurs that actually slows this thing down. And it turns out, it's a complicated calculation to do, but it turns out that that electrostatic repulsion is exactly the same size as this magnetic force that we can calculate sort of simply by thinking about a current moving in a magnetic field. So I know that's not terribly satisfying, but it really is the case that this magnetic force isn't doing work. It's the electric force that's doing it, and it's a result of this combination of changing of the magnetic field producing an electric field and the trajectory that the particles actually take, which is not a straight line trajectory because they both move to the right and up. All right, so in this video what we did is we went into detail about this negative sign, talked about sort of how that gives rise to a current that would run around a setup like this, and how that satisfies conservation of energy by slowing the rod down, slowing the bar down as it moves across. And so that minus sign is really important because it both tells us the direction of currents that would develop in these kinds of situations, but it also clearly satisfies conservation of energy.